atlases. Recall, we said that two charts, for example, phi u, psi v, are compatible. But now explaining what phi u and psi v is, we assume all those the charts. Infinity compatible. Compatible with the transition maps, phi composition, psi inverse, and psi composition, phi inverse are C infinity. Okay, so this is what that we defined out. Okay. Then by atlas we mean the collection of maybe by C infinity atlas simply atlas, I mean that it's a collection phi alpha u alpha some index set I is a collection of C infinity compatible charts. Okay. So we discussed all these in greater detail, what these are, why these are, okay, why you need all this basically in yesterday's lecture. I'm not getting into it again. By C infinity atlas, I mean a collection of the charts that contains in which all charts are C infinity compatible. In other words, the transition maps are C infinity compatible, and obviously must satisfy a crucial condition that if you combine all these open sets actually, okay, alpha and I u alpha, they cover the whole manifold.
Sir, so if you pick any one element, any one chart from this collection, it will be compatible with all others.
Other charts, yes. So they are mutually compatible with each other. C infinity compatible. But as I said yesterday, that it could be C1, C2, or anything you want. So you should have compatibility, and all these open sets should combine give you the whole manifold. In other words, you can cover the manifold using these open sets. We did one example of the circle S1, so we created one atlas for it. Let me prove a lemma that we left yesterday, and we said that we can do it today. And this lemma is going to have some very interesting consequences. So here is, so basically what we are heading. We are heading towards defining what we mean by a C infinity manifold. So we have defined a topological manifold, we didn't know it on that. But what we mean by a C infinity manifold, so all this is a preparation to define what you call the C infinity manifold, and we're going to do some examples. Okay. So imagine you have a collection of C infinity compatible charts, it's an atlas. Okay. So it's an atlas for M. Okay. If I have, and by atlas I'm always going to mean C infinity atlas. Okay, so shouldn't be atlas for M. Now if I have two other charts, maybe give them a name, okay, psi V and maybe sigma W. Okay. If we are two charts, they are compatible with atlas. Compatible with atlas. By compatibility, I mean C infinity compatible with atlas. Okay. Then these two charts, psi V and sigma W, are C infinity compatible with each other. Okay. What do I mean by that? Okay, so these two charts are C infinity compatible. In other words, if I take any chart from here, atlas, and I check its compatibility with this and this in this sense, then they will be compatible. And now what I need to show that these two charts are C infinity compatible themselves. It should be easy, think about it. If this and this is C infinity compatible, okay, so it's like one of the chart here is C infinity compatible, then, and I also know that this and this is C infinity compatible, okay, then I can make a commutative diagram in such a way that the transition maps, okay, from this chart to this chart or this chart to this chart are also C infinity. It shouldn't be a difficult thing to do. So here's the thing. So what I need to prove basically essentially, in order to show that these two charts are compatible, I need to consider the transition maps. So we need to show, okay, the psi composition sigma inverse and sigma composition psi inverse are same. Okay, this is what. So I'm going to show one of them and that you can see it for yourself. How I'm going to do it is simple. So imagine this is my V, okay, and this is my W. Okay, that's V, W, and this is one of the elements from the atlas actually. Maybe say U alpha, phi alpha, U alpha. Okay, maybe I must write it correctly. Must put the map first and then open sets afterwards. So phi alpha, U alpha. So this is, what do you say, is U alpha. Okay. Now, this would be what? So this part, okay, this marked part. So it's going to be the intersection of all these three open sets. Are you getting the point? Now, if I pick a point from here, say this point is P, using the charge map of, since this point lie in, what do you say, V, so using the charge map of V, which is psi, I can send it into the Euclidean space. Okay, I can send this point into this point P into psi of P, which is going to be a point in Rn. Okay, and since this is also a part of W, so I can send this point to sigma of P. Okay, the point is P. And then since this point is also a part of, what do you say, U alpha, I can send this point to phi alpha. Is it making sense? Now, can I go from, so these are the coordinates of this point, okay, with respect to the psi, and these are the coordinates of the point P with respect to the chart map phi alpha, and these are the coordinates of the P with respect to the chart map sigma. In other words, can I go from this coordinate to this coordinates? Can I go from these coordinates to these coordinates? So which are the maps which will take me from one coordinate system to another coordinate system? So it's going to be the transition map actually. So what transition map will take this point and throw it here? So it's gonna be psi inverse composed with a psi inverse after phi alpha. Take the point. And how about this one? Okay. So this is going to be sigma composition phi alpha inverse. Okay, this is going to be the case. Alright. Now I would like to ask from you. And now we are in position to do what we want. This guy, psi composition sigma inverse, is a map from where to where?
Psi of phi of P. Psi of P to psi
It's a
of
map from where to where?
sigma of P to psi of P, sir.
So the sigma is sending. Okay, so sending. This is an element in sigma of U alpha intersection V intersection W. In it. That's a point here. Because this point is what? U alpha intersection V intersection W. So sigma is sending this thing into this cell. So the sigma inverse is going to take an element from here and send it to the intersection, and the psi is going to send it into this basically setting. And this is an element where? So it's the psi of U alpha intersection V intersection W. Okay. So to be precise, this is a map of sigma of U intersection V, U alpha intersection V intersection W into psi of okay, U alpha intersection V intersection W. Okay? So this is what is. So we need to see explicitly that what this creator is. So now we can see that what this map is. Now why this is C infinity is pretty simple. I can do what?
This can be written as
I can put, for example, psi composition. Okay.
phi alpha.
Phi composition, phi alpha inverse. Composition, phi alpha composition,
Sigma.
sigma inverse. In other words, if I want to reach from here to here, I have two ways. Either I go backward by sigma inverse, okay, and reach here, and then go to this point by psi. I have other way, and the other way is that you take the sigma inverse, okay, I can reach from this point to this point by using this one. This is what you call horizontal path. Again, both should be same. Both should be same. Take us on. I can go backward. Now this guy is what? That's a transition map. And now, since this psi v is compatible with phi alpha u alpha, so this map must be C infinity. This is a C infinity map, by definition. And this is a transition map also. Since again, the sigma w and phi alpha u alphas are compatible. So that's a transition map, and this must be also C infinity. And since both of these maps are C infinity, so their composition is also C infinity. Hence psi composition sigma inverse is C infinity. Similarly, I can also show
Psi of
sigma composition psi inverse is C infinity. Okay? And if you want to show that two charts are C infinity compatible with each other, just show
these two.
that these two transition maps are C infinity. So you show that. That's it. Okay? Is it making sense? Okay. That I have two charts which are compatible with Atlas, then those two charts must be compatible themselves. Okay. Are you getting this one? So let's move now
The
towards
equivalence relation.
what do you mean by it is going to be kind of an equivalence relation. Yes, it is going to be kind of an equivalence relation. Okay? Fun to think how to define that equivalence relation and how to prove it. But it is that.
the
Yes.
relations compatible.
Something looks like this. So after this lemma, we are in position to define what I mean by smooth manifold. Okay? The key there. Okay? Smooth manifold. You can also call it C infinity manifold. Or you can call it a manifold actually, simply. So whenever we say manifold, we mean smooth manifold, or C infinity manifold. And this species is a bit different from topological manifold. So you have to be a bit careful. Okay? It requires some extra structure. Okay? I can't play much on topological manifolds, but I can play on C infinity manifolds. Because on topological manifold, smoothness is an issue. Defining linear maps is an issue. Okay, hence defining differentiation, okay, and doing calculus is an issue. But since if you are on smooth manifold, then this is what you call the species on which you can, do whole calculus, entire calculus on it. Okay? And you can learn a whole subject of advanced calculus that is going to be probably how to do the calculus on manifold. This is not a topic of differential geometry, but yes, you can learn a whole entire course on how to define, how to do differentiation on manifolds, how to do integration, what would be the different version of Stokes theorem, and different kinds of things. So you can do all that. Anyway, so what do I mean by smooth manifold? So a smooth manifold is a stronger condition than being topological manifold is topological manifold with maximal atlas. Okay, what does it mean? I'm going to define it. With a kind of an atlas. So if you have a topological manifold and you have atlas on it, okay, then, and that atlas is, since we say that atlas is C infinity, okay, so you're going to call it a C infinity manifold. But imagine you want to define C2 manifold. Then you require your atlas to only be C2 compatible. And you want your charts to be C2 compatible. Okay, so it's not something special about C infinity. you can do this as well. But since we want to do things freely, so we can assume C infinity. Okay, so if I have a smooth manifold, if I have a topological manifold and an atlas on it, think about it. What does it really mean? So you have an abstract space, which I have no idea how does it look like, and I have an atlas on it. And what the atlas is going to do? Atlas is going to cover that abstract space with open sets. Okay? In other words, the charts actually. Okay? And then I can take a piece of that abstract space, that is the chart, and since I have a chart map with it, so I can take that piece of abstract space and throw it in Rn. And do your analysis and calculation in Rn actually. So we know how to do vector calculus. Okay? And hence you can understand the things in that piece of abstract space by understanding its projection or its map or its image in Rn actually. Are you getting the point? Okay? And now, okay, since all these what you call charts which cover your manifold, okay, are compatible with each other, so anything that you conclude in Rn can also be easily understood, or a similar kind of thing is also going to hold on manifold actually. For example, here's the thing. For example, so there's a particle or maybe a bird that is moving on your abstract space, okay, for which you have no idea that how does it look like. Okay. So what I'm going to do, I'm going to take that path. Now that path that what you call object is following is not, okay, it can lie in one chart, but it can also lie in combination of charts actually. Okay, I can fly from, so it's not necessary that I'm going to only fly within Pakistan actually. So I can go from Pakistan to some other places. So one chart to another chart. Okay. So my trajectory can be of the multiple charts. Okay. Now I can take that trajectory, okay, and throw it into what do you call it, in Rn. So when I'm going to throw it in Rn, I'm going to have, for example, okay, two open sets in Rn in which I'll have a curve. It's not necessarily looks like the original curve on manifold, but it's going to be some kind of curve. Now I can compute its velocity, acceleration, energy. You can do all kind of physics or whatever you want to do with that, particle or that bird, okay, that you want to know in Rn. Okay, once you have that, the similar set of information would also be valid for the original, what do you call it, bird and so on, and the trajectory on that. So this is what essentially the trick is. Okay, this is what essentially the trick is. But all this can happen if you have charts which are playing nicely with each other. So why I'm taking an atlas, which is kind of C infinity compatible, is that, okay, the charts are behaving in a good manner with each other. As I know, okay, if something is, so one chart allows you to differentiate the curve, but other chart doesn't allow you to differentiate it. ठीक है, एक जगह differentiation कर सके, दूसरी जगह ना कर सके.
Overall space नहीं कर सके. Overall space with मसला.
Yes. So if they are smooth, okay, are of similar, then you can do your calculation in any chart you want. In other words, your calculations are going to be not chart dependent but chart independent actually. Okay. ठीक है? What's maximal atlas? Okay, so I'll define it technically. Let me give you intuition. So if I have a manifold, again, I talked about it yesterday as well. So it's like I have a topology of it. So that means that I have a lots and lots of open sets, okay, that are covering
covering all of it.
This entire M. Okay. Now this atlas, okay, in which you have all kind of charts, okay, with all kind of properties, okay, and that are covering M, you're going to call it. So that's the kind of the, okay, so you want to cover M, now you are covering M with necessary and unnecessary things as well. Okay, are you getting the point? So in this chart there are, okay, in this maximal atlas, you're going to have charts in which you can do differentiation, and you're going to have charts in which you can't do differentiation. Okay, in this maximal atlas, because it contains everything, all kind of charts. But what we want to do, we want to kind of rectify this chart. Okay, so I want to throw away the extra bits, and I want to have a cover. Okay, atlas, I'm talking about atlas. Sorry. So I want to rectify this atlas in such a way that, you know, I can get what you call a C infinity or whatever regularity I want, or what are C infinity or C1 or C2, you know, compatible, what do you call atlas.
सर ये लाजमी तो नहीं है हर manifold को find कर सकेंगे.
You can always find this maximal atlas. Okay, but how to find it? Interestingly, we're going to prove a result which is going to show that if you have an atlas for a sphere, okay, then for this given atlas you can find always a maximal, unique maximal atlas. Unique maximal atlas. So for a manifold, you can't have more than one maximal atlas. Now imagine you have two atlas. One of the things is that for a manifold, it's not necessary that you should have just one atlas. You can have multiple atlas. So I want to cover a circle. I can cover it by, you know, two, you know, half circles. Okay, or I can cover it by four, you know, quarter pieces of circles, or I can take four half circles, okay, one top down and one, you know, from this side, and I can cover the circle. So in other words, you can have multiple atlases for one manifold. Okay, I get my point. But all these multiple atlases are going to eventually fall into a unique atlas. You getting the point? And that unique atlas would be, you know, something called the maximal atlas. Okay. So we're going to show that we don't always need maximal atlas. You only need a simple atlas. If you have a simple atlas, you can always find a maximal atlas. So in other words, so I'm going to prove, so at the moment definition requires that you must have a topological manifold and you must have a maximal atlas. Now this is a lot restriction actually. Okay? But I'm going to prove, you know, a result that is going to make it weaker, which is going to show that if you have some atlas on a topological manifold, then you can have a maximal atlas.
Sir, maximal atlas की rigorous definition क्या है?
So let's put the rigorous definition of maximal atlas. Are you getting the point? But this is important that we must understand that what we are doing. Okay? And essentially what I want to do, I want to introduce you to the several examples of the smooth manifold. मैं चाहता हूँ उसके बाद we'll leave all this discussion and we'll return back to what we were doing. What I want is that at least you must have a very clear picture of manifold in your head. Okay? So what's a maximal atlas? Achha, this maximal atlas is sometimes also called differential structure. Okay?
Yes, sir.
It's also sometimes called differential structure.
मैंने ये जवाब आज मैंने तो ground